Hello everybody, my name is Iman at SID. Welcome back to my YouTube channel. Today we're going to continue and finish chapter 10. And we're going to start our lecture today by defining two important terms before continuing any further. These two terms are radical inhibitors and radical initiators. Now, radical initiators are substances that generate radicals. It is a compound with a weak bond that undergoes homolytic bond cleavage with greater ease. A good example of a radical initiator are alkyl and acyl peroxide. That oxygen-oxygen bond in both alkyl and acyl peroxides is a weak bond, which contributes to why they are both successful radical initiators. That weak bond is easily undergoes homolytic bond cleavage. Now, radical inhibitors inhibit the formation of radicals. These are compounds that are going to prevent a chain process from either getting started or continuing. So last time we saw chlorination of methane, and we looked at the radical mechanism for how we can take methane and substitute one hydrogen with chlorine. You can actually, with excess chlorine, substitute all the hydrogens with chlorine. All right. Now, what can help prevent that chain process from undergoing or continuing is using a radical inhibitor. Now, an example of radical inhibitors include molecular oxygen and hydroquinones. These both are able to couple with other radicals and destroy them, hence preventing chain processes from either getting started or continuing. So please keep these two terms in the back of your head. They might reappear later in our discussion. But for now that we have defined those, we're going to move on to radical halogenation. Here we want to ask this question. Just like radical chlorination, which we saw in our last lecture, worked through the mechanism and all, is it possible to achieve radical bromination, fluorination, or iodination? We can get the answer to this question by exploring the Gibbs free energy of each. And this is going to help us determine what reactions are thermodynamically favorable or not. So let's refresh on Gibbs free energy equation. It equals our Gibbs free energy here, delta G, equals the change in enthalpy, which is our delta H term, minus temperature multiplied by the change in entropy, shown here as delta S. Now, since we are taking two molecules, like we saw in chlorination, right? Methane and another molecule, whether it be Cl2 for chlorination, Br2 for bromination, F2 for fluorination, or I2 for iodination, we are starting off with two molecules and we're going to end up with two molecules. All right. So since we are starting and ending with equal amounts of molecules, starting off with two molecules, ending with two, the entropy component in our Gibbs free energy equation is actually going to be pretty negligible. This is going to be pretty negligible. And so what that means, negligible, I can't spell that. What that means is we can essentially write that our Gibbs free energy is approximately equal to our enthalpy. All right? So that means we're going to focus on the enthalpy term to determine whether radical bromination, fluorination, or iodination is possible. So finding the change in enthalpy experimentally for all, focusing on the bond dissociation energy, we realize something important. We realize that all the processes are exothermic except for radical iodination. So chlorination, bromination, and fluorination, all right, are all exothermic reactions. All right, what that means is they're going to have a negative delta H. And if our Gibbs free energy is approximately equal to our enthalpy, that means we're going to have a negative delta G, which means thermodynamically favorable, spontaneous reaction, right? So if chlorination, bromination, and fluorination are all exothermic, that means that they're all possible reactions except for iodination because it's endothermic. Now, that's almost true. Fluorination, although exothermic, is actually way too violent for practical lab use. So, although spontaneous, although thermodynamically favorable, too violent for practical use. So what you actually do in lab setting, is chlorination and bromination. And these are the two radical halogenation processes that we're going to focus on for the rest of this chapter. Fluorination is too violent for practical use, and iodination is not thermodynamically favorable. So in conclusion, only chlorination and bromination are practical in lab. Now, we observe the energy diagram for chlorination and bromination. Here, I'm going to erase some of this stuff so we can take a good look at this diagram. What we're observing is the energy diagrams for bromination and chlorination for the propagation steps. And we realize that the rate determining step is the first step in radical halogenation. That's going to be our hydrogen abstraction for both of these. So the rate determining step is the first step in propagation. It's going to be exothermic for chlorination and endothermic for bromination. All right, so one more time. What we're observing is the energy diagrams for chlorination and bromination for the propagation steps. We realize that the rate determining step is the first step. It's exothermic for chlorine and endothermic for bromine. Now, even though that the general complete process for both is exothermic, like we initially said, right? Compare start and end. They're both exothermic processes. Bromination is actually going to occur a little more slowly than chlorination as a consequence of the rate determining step. Now, when a molecule undergoes radical halogenation, there are sometimes two or more possible products. What we see here is an example of chlorination and bromination. We're going to take a good look at both of these. All right. The topic of selectivity of halogenation is actually going to allow us to predict product distribution. What is the product distribution and how much of each product to expect, whether it's for chlorination and bromination. And the objective here is to understand the difference between product distribution for chlorination and bromination and be able to distinguish between major and minor products. Now that we've stated our objective, let's look at these two examples. Let's look at bromination first. All right, we're starting off, all right, with this 3-carbon chain, all right? And we're treating it with Br2, this propyl group. I kind of blanked out at the name of this propane. So sorry, I said 3-carbon chain. We're starting off with propane, all right? We're treating it with Br2 and light, all right? Indicative of a radical reaction here. Now, what can happen is that we can have a hydrogen abstraction in one of two places, here and here, and that's going to result in a radical, and that means that we can actually add bromine to these two sites. All right, in short, we don't have to draw the whole mechanism for us to understand that there are two possible sites for the bromine to attach to. All right, and those two sites. Now, if we add bromine here, we get this product. And if we add bromine here, we get this product. Now, the major product is going to be this one with 97% yield as opposed to this product, which is at 3% yield. All right. Now, the reason for why this product is the major product for bromination has to do with the rate determining step in the first propagation step, that hydrogen abstraction. For bromine, this rate determining step is much slower and it's endothermic. It's going to prefer this product because it forms a radical that is more stable, a secondary radical as opposed to a primary radical. And because of its endothermic rate determining step, the product obtained from the more stable radical is going to be the major product. All right, now for chlorination, this is a different story. All right, here we're starting with propane. We're treating it with Cl2 and light or heat sometimes. All right, indicative of a radical mechanism. Now, again, two sites where chlorine can be added, here and here. Now, if you add chlorine to this first orange site, you get this product. If you add chlorine to this site, you get this product. Now, notice how this is still the higher yield, but they are very close, 60-40. And sometimes it can even border being very, very, very close. All right. Now, again, this has to do with the rate determining step. For chlorination, that first rate determining step is exothermic. So both sides are really chlorinated fairly equally. All right. So one more time. Here we see an example with radical chlorination and bromination. And this topic of selectivity of halogenation is important because we want to predict what the product distribution is and how much of each product to expect, like we just discussed in this example. Our objective was and is to distinguish between major and minor products. How were we able to do that? Easy. We're going to use our stability order to determine major products, keeping in mind our order of stability for radicals. That's the first thing. All right. Second, the discrepancy, even though we know that our major product is the one with the more stable radical form, all right, we want to recall that the rate determining step in the first propagation step, hydrogen abstraction, also plays a role in the difference between yield of our two products. All right. A more stable radical form is going to result in our major product, but the discrepancies between bromination and chlorination is different in yields because of their rate determining step, where chlorination it was exothermic and for bromination it was endothermic, that rate determining step. Now we can further observe this by investigating the energy diagram, all right, showing the abstraction for primary, secondary, and tertiary radicals in chlorine and bromine processes. So let's look at that. In each step, in each transition state, actually, an unpaired electron is developing on a carbon atom. The developing radical is always more stable on tertiary, then secondary, then primary. So all of these reasons, all right, to say that bromination is said to be more selective than chlorination because of that rate determining step. That hydrogen abstraction in bromination is endothermic. And look at the discrepancy in the energy required to form a product from a tertiary radical, a secondary radical, and a primary radical. Is quite a bit different between the two. Hence why the product for the more stable radical is at such a greater yield than for the less stable radical, right? When we formed our two radicals from our propane that we're trying to brominate, the more stable radical, which is our secondary radical, is going to form the product at a greater discrepancy than our least stable radical, and is because of this energy difference between doing the hydrogen abstraction in the bromination process. Now, for chlorination, the energies are so close together, whether it's a primary, secondary, or tertiary radical that is being chlorinated, the energies are so close, so there is more of a blurred line in terms of what products you're forming, which is why even though your major product is still the more substituted radical, there is less of a discrepancy between the yields. They are closer together. And so bromination is said to be more selective than chlorination, right? Because of this endothermic versus exothermic rate determining step. And during bromination, the amount of radical character at the transition state is greater than in chlorination. And as a result, the transition state will be more selective to the nature of the substrate during bromination. So that is very important to keep in mind. Fantastic. Let's do a quick practice problem. Predict the major product obtained upon radical bromination of each of the following compounds. All right, so looking at A, not highlighter, let's do pen. A, we have a tertiary position right here that has a hydrogen that can be abstracted to form a radical right there, ultimately, that can be brominated. All right. Now, you can do it at this site as well, and this site, and this site, and this site, but they're going to be tertiary. They're going to be secondary carbocations. This position's a tertiary carbocation. Radical. So these positions would, if you do that hydrogen abstraction, would form secondary radicals, not carbocations, sorry. Whereas this site right here, through hydrogen abstraction, would form tertiary radical. That is obviously more stable than secondary radical. That means that our more preferred product would be formed at that position, because remember, bromination is very sensitive to the nature of the substrate. And so our major product for this would be adding a bromine to that tertiary radical position that would happen after hydrogen abstraction. All right, let's do B. Is there a place where we can do a hydrogen abstraction that results in a tertiary radical? Yes, we can, right there. And what that would form is something that looks like this, that we can then treat with Br2 and light or heat, and what we would get is a bromine added at that site. Fantastic. I'll let you attempt to see. Let me know what you get in the comments below. But we want to talk about one more big topic for halogenation, and that is stereochemistry of halogenation. Now, if halogenation creates a new chiral center or occurs at an existing chiral center, we're going to expect a racemic mixture of products as we see in these two examples. All right, if we chlorinate this molecule, all right, you can add a chlorine at this site or this site. They are equivalent sites, by the way. You can add a chlorine here, but if you do, you formed a chiral center here with 4 different groups attached to this carbon. What that means is you're going to get a racemic mixture of products where you're going to get both R and S configuration. So the chlorine can be both on a wedge and a dash. Of course, you're also going to get the product for primary radical formation here. So yes, you can form a secondary radical here where you can add the chlorine. You can also form a primary radical here and add the chlorine here. This would also still be a product. All right. Now, if it exists, if you're doing halogenation at an existing chiral center, all right, you're still going to get a racemic mixture of products, and you want to make sure you draw this appropriately. So whenever you're adding the bromine here, the bromine will add both on a wedge and on a dash, both in R and S configuration. All right. Now, if there is already an existing chiral center that is not involved in the radical halogenation, so it's another site on the molecule that is a chiral center, the products are going to be called diastereomers. All right. So you're going to do radical halogenation at this site because it has a hydrogen here. All right, Br2. And it's going to be your most stable radical form, right? Because you're going to get a secondary radical here, whereas a primary, remember, we're doing with Br2, so we're just going to really focus on that more substituted radical. All right, so we're going to be adding our bromine here. There's already a chiral center somewhere else. So we're still going to be drawing our bromine on wedge and dash, but these are no longer racemic. They're not enantiomers. They're diastereomers because there's another chiral center somewhere else. All right. Now, if you've forgotten the difference between enantiomers and diastereomers, I know it's been a while since you're in OChem 2 and near the end of the semester probably now. If you need a fresh reminder of that, visit chapter 5 of my videos to touch up on that. But anyways, let's do a practice problem now that we've discussed stereochemistry of halogenation. Here in this problem, we want to predict the stereochemical outcome of radical bromination of the following alkanes. So A is easy. All right, here we have a place that if we abstracted a hydrogen, we would form a tertiary radical. And that's where our bromine is going to be added. Now, when we add a bromine there, do we have a chiral center? No. So we're not going to get a racemic mixture. And also, there are no other chiral centers in this molecule. So this is our product, all right? Our major product. Now, if we look at B, all right, the place where we could do hydrogen abstraction and get the most stable radical is right here. If we do a hydrogen abstraction, we'd get a tertiary radical. All right. Now, if we add our bromine there, if we add our bromine here, we're forming a new chiral center. What that means is we're going to get a racemic mixture of products. And so that means we want to draw our products appropriately. We're going to have our bromine on a dash and our bromine on a wedge. And these are our two products for this racemic. Fantastic. Let's go ahead and also do C. I will leave D for you. So let's do C. Now, if we do a hydrogen abstraction here, we'd form a tertiary radical, which would be very stable, and that's what we want because we're dealing with radical bromination. We know how picky that is. All right, so we're going to be adding a bromine there. If we add a bromine there, we formed a new chiral center. All right, so we want to make sure we draw this appropriately because we're going to get a racemic mixture. That means our products are going to look like this, where our bromine's on a dash and our bromine is on a wedge. Like so. And these are our products. Racemic mixture. Fantastic. Now, all the examples we've done so far and talked about in regards to radical halogenation can actually occur with alkenes as well. They're not specific to alkanes. Now, when an alkene undergoes radical halogenation, say bromination with Br2 as a reagent, a competition occurs between allylic bromination and ionic addition of bromine across the pi bond. All right, so if you have something that looks like this and you treat it with Br2 and light, you're going to have a competition between adding allylic bromine and then also simply just adding the bromine across the pi bond and completely losing the pi bond. You're going to have that competition occur between allylic bromination and ionic addition of bromine across the pi bond. To prevent this, we have to use a different reagent for radical bromination of alkenes. This reagent is called N-bromosuccinimide, or in other words, in shortened, NBS. NBS looks something like this. This is gonna be a very, very useful technique that we're gonna use and reuse for synthesis problems down the lines. If you only want to take an alkene and do allylic radical bromination, then you do not want to use Br2 as a reagent because you're going to have a competition between radical halogenation and just plain halogen addition. What you want to use is NBS so that you are only getting the product for allylic bromination. Now, still, mixed products are possible if you do allylic bromination. What happens here when you use NBS is that you're going to have a hydrogen abstraction here, right, in the allylic position. And that means that you're going to have a radical that forms right here. But hey, that's an electron near a double bond. You're going to have a resonance structure because of that. So whenever you draw the resonance structure, both of these resonance structures can undergo radical halogenation. So your bromine can add to both of those positions. Hence why mixed products are possible when you are doing radical halogenation with alkenes. All right, now this is best understood by doing a few practice problems. So that's exactly what we're going to do. We're going to do a few practice problems where we're going to predict the products when each of the following compounds is treated with NBS and light. All right, fantastic. Looking at this first molecule, A. All right. Let's look at it. We're going to identify the allylic positions. All right, so here's our double bond. All right, we know that the atoms participating in the double bond, those are vinlic positions, not what we're looking for. Allylic are the next atoms attached to those. So we have 4 allylic positions. These have no hydrogen, so we can't do a radical reaction there. But we have these 2 that do. All right, now they're both identical, right? Because this molecule is symmetrical. So both of these positions are identical. We're just going to work with one because they're both going to result in the same product. All right, so looking at this allylic position, all right, through hydrogen abstraction, what's going to happen is we're going to form a radical right there. All right, we're going to go ahead and draw that. All right, now you have a electron right near a double bond. We're going to have a resonance structure here. All right, that resonance structure is, well, you can take this electron, dump it here, and 1 electron of the pi bond and form a new double bond here. This extra electron gets dumped back here. And now we have our resonance structure for this molecule that is going to look like this. All right, fantastic. And let's not forget these extra right here. Now, both of these can produce products. All right, your bromine can attach to this position right here, and that product will look like this. Bromine right here. All right, or radical bromination can occur at this radical site right here. And what our product would look like if that occurred is as such. So these are the 2 products we would obtain for radical bromination of alkenes as we see here. Let's do one more. Let's do B, and I'll leave C and D for you to figure out. All right, fantastic. What do we want to do here? Well, we want to look. We have a double bond. We're treating with NBS and light, so we know we're going to be doing radical bromination of an alkene. We want to identify our allylic positions. Here's one and here's one. This one's not important. There's no hydrogens here, but there is a hydrogen right there. So that hydrogen is going to be abstracted, right? It's going to be stolen, and what we form is a radical at that position. Now, you have a lone electron right next to a double bond. We're going to have resonance structure, so we need to draw that. Well, you can form a double bond here, and this extra electron will be dumped there. And that means we're going to have a radical in a new place. Now, let me draw this appropriately. both of these molecules are going to produce products. If your bromine gets attached to this, from this radical, if we treat this with NBS, our bromine is going to be added right here. So our product will look like this. Fantastic. Now, from this, if we treat this resonance structure with NBS, our bromine is going to attach here. And so our product is going to look something like this. Bromine. Fantastic. These are our two products for this reaction. Fantastic. I'm going to let you do C and D. Let me know what you get or if you have any questions. But to end this chapter, we want to talk about radical processes in the real world. One of the most prominent examples is the ozone. Ozone is produced and destroyed by radical processes that shield the Earth's surface from harmful UV radiation from the sun. The use of things like chlorofluorocarbons in things like refrigerators ultimately had such a negative effect on the ozone that they had to be replaced with HFCs. Now, radical processes are also used heavily in the chemistry industry, particularly in the petrochemical industry. And so radical reactions are used in cracking and reforming. When cracking is performed in the presence of hydrogen, it's going to be called hydrocracking. And these are all ultimately radical processes. So, just to put this in perspective, these radical processes are in a lot of the chemistry, the chemical industry, and in the environment. So with that is the end of the chapter. Let me know if you have any questions, comments, or concerns. Feel free to reach out to me if you need any help at all. That's what I'm here for. I love helping. Other than that, good luck. Happy studying. Have a beautiful day.